From analog.
Hi, Jim. You have a great signal up here. You're 5.9 plus.
You're digital.
We are everywhere you want to be. This is the CQ Blind Hams Podcast.
Okay, I'm back. So yeah, basically at this point, everybody's been muted. So unless you are a co-host or a presenter, everybody else, please stay muted and stay that way until, opportunities will be given to make comments, ask questions, and things like that. So let me flip over here and get to my notes. All right, good evening, everybody, and welcome to the July edition of the Blind Hams, the CQ Blind Hams Tech Zoom. I guess you can kind of think of it as the interactive version of the CQ Blind Hams podcast. If you don't know by now, this meeting is being recorded. You should have by all gotten some alert to that effect now. So if you, for whatever reason, do not wish to be heard on a recording that will eventually become a podcast, then I guess you'll probably just want to stay muted for good. You have to accept by pressing the button that says "Got it." That's on that alert that should have shown up telling you that the meeting is being recorded. You got to do that, otherwise you will not be able to access the meeting controls. And if you do plan to speak, you will want to have access to your meeting controls. So again, anybody who is not co-host or presenting, stay muted. When we do open it up for comments, questions, etc., wait to be acknowledged before you go forward with your comments or questions. The whole idea is to kind of not wind up in a situation where we're all talking over each other and cutting each other off. All right, so without further ado, I will go ahead and introduce fellow co-host and crew here of the CQ Blind Hams Tech Zoom. We'll go with Joel, W0CAS.
Thank you, Julian, and everybody, and welcome to one of our first Tech Zooms. It's going to have a guest speaker other than one of our own co-hosts. So we're looking forward to this talk coming up.
Yeah, same here. I think it's going to be a very interesting topic, and hopefully in the future we will be able to have more guest speakers as well. Robert, NC5R.
Good evening, everybody. Speaking to you tonight on a portable rig from Little Rock, Arkansas, not my normal Texas location. Excited to be here and looking forward to this presentation. Thank you, Julian.
And thank you. Steve, WB2K-TV.
Evening, everybody. Calling from New York City, the noise capital of the universe, both RF and otherwise. Looking forward to learn how to quiet it down a bit.
That is for sure, on both counts. And in the back there, running the controls and making sure everything sounds good, Angelo, N2DYN.
Welcome, everybody. Happy to help out, and I hope you all enjoy it.
And last but not least, you have me, Julian Vargas, call N1CA out of sunny Southern California. Okay, so without further ado, we're going to go ahead and introduce our guest speaker today. His name is Bob Brem. His call is AK6R. He's going to be discussing or giving a presentation that I believe he calls the ABCs of RFI for hams. Bob's been a ham since 1963. He's currently the chief engineer at PalomarEngineers.com. That's www.palomar-engineers.com. And on that website, you'll find all kinds of neat little things from antennas, RFI kits, ferrite beads, toroids, and interestingly too, downloads of previous products, that manuals and such. There's also lots of hints for antenna installations. There you go, if I could speak. Dipoles, landline outlets, and neat things like that. He has given lots of presentations at ham ventions, get-togethers, those kind of things. And those are all available, or some of them are available there on that website. He is also available to do what he is doing here, giving a Zoom presentation to ham clubs out there. So if anybody's interested in booking Bob to give a presentation for your ham club, go ahead and reach out to him via email. His contact info is available on that website. So without further ado, we'll go ahead and send it over to you, Bob. Give us this wonderful presentation that we're all looking forward to.
Okay, well, I hope I can keep the expectations up, of course. So the first thing I'm going to do is I'm going to share the screen, and then I'll go through some of the history of Palomar Engineers for those of you who don't know. So I'm going to go over here and share my screen, make sure I got the right program. I was going to talk about antennas tonight, but I just did RFI last night. So it doesn't say the Blind Hams on the bottom. It says Valley of the Moon Amateur Radio Club, and that's a radio club up in Northern California in the wine country, and they call it the Valley of the Moon. And we gave that one last night and had a good time doing that. So anyway, tonight we're going to be talking about the ABCs of RFI for hams. There's my information right there, palomar-engineers.com. Give you a little bit of background here. Can everybody see that, by the way, or at least is aware of it? Okay. A little bit about the history of Palomar. It was founded in 1965 by Jack Althouse, K6NY. And if you were a reader of CQ magazine, you may have read about him under his pen name, which was Kurt Sturba, again, Sturba antennas. And in fact, he had a whole line of books, and he wrote an article every month for CQ for almost 40 years. He was and they were funny, and they were pretty good at attire and comedy of amateur radio and in general life. So they're fun to read. They are available free for download on the website, and you just got to look for the word Kurt Sturba, KURTSTERBA. Anyway, Kurt passed away, and Jack passed away in 2013, and his kids didn't want anything to do with the company, and so they had moved it into a storage area 10 feet by 10 feet. And I went over there and told them that I was interested in buying it, and so my wife and I bought it. We turned it into a woman-owned business for business purposes. And we went and bought the entire company. And to this day, I still have all the original engineering drawings. And there's over 3,000, and they're all in pencil because he made changes in pencil for all of them. And just a wonderful history. He had about 400 different products, many of which were copied by MFJ in the mid 80s. And have been copied by other people along the way. But he was quite an innovator. He passed away at the age of 92, and he was still very active CW operator running a TR4 from his apartment, his girlfriend's apartment, I should say. Okay, so our product line, we decided to change the company and reorient it towards RFI solutions. And some of the products obviously include ferrites, which we're going to talk about tonight, show you what they are, and also explain them to you. But we also do things that are made out of ferrites, and those are ballons, ununs, feed line chokes, and those types of things. Also antenna systems. We now sell antenna systems all over the world, and we distribute through Ham Radio Outlet directly, and we're also on eBay at this point. But we also came up with a whole variety of RFI solution kits. So, for example, if you're transmitting on your radio and the touch lamp goes off in your wife's room, for example, or you're interfering with the home theater system, or your sprinklers are going on and off the CW pulses like mine did when I first moved into a new house. There's a solution kit to solve that problem. You don't really have to know the technical aspects of it, but you have to be able to take some ferrites, snap them on various places on the device that's either the source of the problem or the victim that has a problem on it, and then just put those on there, and by magic, the problem usually goes away. So we distribute to consumers, like I say, ham radio outlet. We do a lot of commercial work. We do also a lot of military. As a woman-owned business, we do get a lot of military business from all over the world, different command posts and things like that. All right, so let's talk a little bit about RFI. Somebody was mentioning spouse approval. Well, this is my ex-spouse on a good day, and it was always a problem because I was the source of the RFI. It was all because of that big antenna that was sitting above the roof. And in fact, I was so good at RFI, we created a couple of awards for it. And one of the awards was worked all appliances. All right, so you may, and this is a fun one. You can download this better. You can download this from the website. And so there's endorsements for 5, 10, 25, 50 appliances. And in fact, I've had people call me back and they've listed the appliances that they interfered with and wanted to know if they could get a different endorsement. So anyway, we've had about 10,000 people download this thing. So it's kind of a fun little spoof thing. And we also have one, if you're really good at RFI, you get a Worked All Neighbors award. Okay, so if you got neighbors around you and they call you up and say, hey, you're interfering with my XYZ, or my computer's slowing down, or whatever, you can download that one. And a lot of clubs will give these out as kind of spoof awards at some of their club meetings, but they're available, they're free. And just look under the downloads portion of the website. But on the other hand, not only are we the source of RFI in this day and age, we're also the victims of RFI. I mean, just if you think about all the different things electronic that are around us, everything from cell towers to Roku machines to automated gas and water measurements now. I mean, they don't even come to your house to measure your electricity or your propane gas. In my case, they just read it off their cell phones, in fact, and via Wi-Fi. But baby monitors, computer routers, wall warts that you plug into the wall, little switching power supplies, they're great noise generators. Anything made by LG or Samsung. Typically the refrigerators, washer, dryers, they're real big noise sources, real easy to fix, but you have to fix them to do it. But all those types of things cause noise, and we see it as a high noise level in our receivers, and or they don't have much filtering in them for high frequency HF below 30 megahertz. And so they are prone to problems from RF that gets into them. And there's lots of ways that happens. And we're going to be explaining tonight how to prevent that, and also how to identify whether it's you causing the problem or something else. So let's go over some of the workshop objectives. It takes about an hour to go through this, and we're about 5-10 minutes into it, so not too much longer. And then we'll have a little Q&A session at the end, and you can ask us questions for as long as you want. Okay, so we're going to talk about radio frequency interference, what it is. How do you identify whether it's something you may be causing, or identify what's causing it to you? How to pinpoint the cause and apply some simple cures. All right. We're going to be talking about ferrite filters. Okay. It sounds like an intimidating word, ferrite, but it really isn't. It's a simple concept. But you have to know how to choose them, how to buy them, and then how to apply them, and where to put them to make sure you solve the problem. We're going to show you how to use ferrites to solve the #1 problem shared by all hams who use coax-fed antennas, which is probably most of us. How to use it to solve transmitter problems, how to use them just to reduce your receiver noise floor, and how to keep your neighbors and your spouse happy. All in that order, by the way. And then I'm going to try and give you the main concepts with little or no math. Okay, you have to know one thing, and that's Ohm's law, but we're not going to be doing any calculations. All right, so let's put our thinking caps on and to go to a definition of what is radio frequency interference. Well, we define radio frequency as anything above about 100 kilohertz, all right? And that means we do not include AC power lines and those types of things that maybe because you have a bad transformer on your AC power or something like that, which could cause problems. We do not include those. It's basically everything above about 100 kilohertz or 100 kilocycles for you who remember those terms, up to about 2 gigahertz. That's about kind of our range, 100 kilohertz to about 2 gigahertz. That covers most of HF and VHF that the hams have access to. It does not cover sunspots, cosmic noise, lightning. There's a whole bunch of sunspots going on right now as we speak, and atmospheric, static, and anything that has to do with AC power lines. So we ignore those, and those have to be fixed with different things than ferrites can actually work on. But we think of all kinds of transmitters. There can be ham transmitters, there can be CB, AM, FM radio stations that you may live close to. Other electronic devices in your home are little transmitters, and they use the power lines of your house as their transmitting antennas, and they can cause all kinds of issues. Inverters, if you have a solar system, switching power supplies, computer electronics. You may have, at least we do in California, we got pot growers everywhere now. It's legal in California to grow pot, right? And so we have grow lights, and grow lights are notoriously noisy, and there's not much you can do about them per se. You can put filters on them, and I've sold a lot of filters to people who actually use them. But as an end user, you have to deal with those types of issues. Common victims of RFI are typically any electronic device that malfunctions, and it works as a receiver of radio frequency interference. In the United States, for all practical purposes, any interference below 30 megahertz is ignored. There's a law against it, but for all intents and purposes, nobody does anything about it. Sometimes you can get the ARRL to look at particular things, but in fact, everybody's concerned about cell phones and higher frequencies in terms of RFI. So it's very difficult to find anybody who can do anything about HF RFI, except of course Palomar engineers, and there's a few other ones out there. So first of all, how do you get RFI? All right, it's not something that you ask for. So how do you get it? We switch slides here. So when you talk about radio frequency interference, there's always a source and there's always a victim. And there has to be a path between the source and the victim. Okay, if we're in a fight, there's got to be somebody throwing the punches, so to speak, to hit the victim. In this case, there's a coupling path between the source and the victim, and it can take the form of about 4 different ways. One is it's radiating through the air. So you have an antenna, it's right above your shack in the garage, for example. It radiates, and you're running a lot of power through it, and the radiation is putting out radio waves, and they're being picked up by the wires that with the associated equipment in your radio room, which may include a computer or something else. Or let's say you have a home theater system and you're transmitting, and you're interfering with the subwoofers and all the other kind of stuff, and so you'll see interference, right? So that's an example of radiating radio frequency interference. It's radiating through the air, it's hitting a wire, and the wire is conducting it into the device and causing a problem. It may be a direct conductivity through wires. Actually, you may have a transmitter and an amplifier hooked together, and the amplifier may be putting out the majority of the RF out the coax, but some of it may be feeding back to the input too, or it may be going through the push-to-talk control circuit that way. On the other hand, you may have just a regular transceiver, and the computer that's hooked to it has some problems. That's because it's feeding back through the USB cable to the radio, for example, or some kind of interface. It could be a capacitive or inductive coupling. An example would be you have an antenna that's in the attic, or you have a coax line that's radiating that's in the attic, and it's next to a AC power line. You're transmitting, and that induces a current into the AC power lines, which then cause interference to things that are plugged into the AC power line. So there's got to be a source, a victim, and a coupling path. And the trick to making and getting rid of RFI is finding the source and the path, and then putting a block in either one of those, and you can cut the RFI out. So let's see some typical symptoms on both sides. So I always tell the story. I had got my ham license in 1963, and I was 15 years old, I think, at that time. And I was playing with AM equipment. And one of the microphones I had was a D104. And I had a old Viking one, and I can't remember what the receiver was, but when I keyed that thing up and I put my lips close to that D104, I got my first kiss, all right? And it just shocked the heck out of me. And I said, if that's what kissing is all about, I'm not in this. But it was quite an experience, I'll tell you. But sometimes you get a hot microphone. What happens is the microphone cable picks up some of the RF. In this case, it was actually coming out of the transmitter, and it made the mic hot, and it sparked my lips. You might, some people would listen to your frequency, and they'd say, you've got distorted audio. And the distorted audio is because RF is getting back in through your audio system somehow, and doesn't make it sound very good. You may experience a high SWR that changes with power. Your coax may be radiating. There's all different types of things, and your antennas will consistently tune differently, different power levels. The SWR will change at different power levels, and that's an indication that you've got some issues there. We'll talk about some solutions for those in a couple of minutes. Your voice or your transmission causes interference with other consumer devices. That could be anything that's acting as a ham radio receiver. And that includes computers, TV audio systems, security systems, garage door openers. Okay, I had a colonel call me from Oklahoma probably about 2 or 3 years ago, and he said, to make the story simple, hey son, I've put some new radio systems in the planes that we fly, and every time they go over this one particular condominium complex, all 100 garage doors go up simultaneously. And I said, well, I got a solution for that. It's our RFI garage door opener kit. So I sold him 100 kits. He had his soldiers put them on, and they never had a problem again. But it's a real common problem. In fact, a lot of people are replacing their fluorescent lights with LED lights these days. And they'll put the LED lights in their garage, and then suddenly they notice that the little garage door openers don't work anymore. Okay, the key fobs don't work. And it's because the LED lights, little switching power supplies, are so close to the garage door opener, it's causing interference into it. So again, you need either an LED filter or a filter on your garage door to stop that problem. But it's a problem that we'll all face one time or the other. The other transmit symptom that's most common is the spouse alarm goes off, and that could be that could be a male or female in these days, I guess. But anyway, what happens is there's a problem, and another person observes it and says, hey, turn the radio off or whatever. I can't watch my Dancing with the Stars, for example. I've experienced that myself. And so I got lots of ferrites on our TVs. That received symptoms that you may experience are caused usually by sources outside your radio. Okay. And we'll show you how to do a little test in a minute that tells you where the noise is coming in. But typically it's a high received noise level, and it's not due to the atmospheric conditions or sunspots or anything like that. It's due to usually it's a wire coming into your radio, and it may manifest itself as either birdies or chirps, or if you have a waterfall on your radio, you can see constant lines going up and down. And I'll tell you a couple of well-known frequencies of RFI. One is 7198. The other is 14198 or 21198. And those are typically solar systems. All right, you'll see this big blurb, and it sits there right around 7196, 7198, and it's there all the time during the day. At nighttime, it goes away. All right, and it's the little inverters that they put on the individual solar panels that are causing that. All right, they're all connected together like a big loop antenna, and they're all transmitting, and they all transmit at that particular frequency. So that's a specific brand, but it's very prevalent I know on the West Coast here, you can hear it all the time. Just tune in to 7198 any day in Southern California, and it's real prevalent. Distorted receiver audio is another thing that you may have if you got a lot of radio frequency interference. So let's talk a little bit about antennas and paths, and that'll allow us to figure out how to reduce that RFI. Typical receiving antennas, if you're having issues on the low bands, and by the low bands I mean 160, 80, 40, typically about 30 meters, 10 megahertz and below. I call that low bands. Well, if you remember your antenna theory, low frequencies require long antennas, all right? Well, interference-wise, it's exactly the same. So you're not going to get 2-meter interference on an Ethernet or on an AC power line, because the power line is not resonant even close to 2 meters. But it's probably resonant on 80 meters or 40 meters or some of the low frequencies. So they act as wonderful receive antennas, right? So when you're transmitting, not only do you want the guy across the country or the person across the country to hear your signal, well, you've got an unknown receiver right there, and it's called your house wiring. It receives that signal as well as the guy across the country. But typically, if you're getting radio frequency interference on the low bands, you look for long antennas that are picking up that energy. And those could be AC power lines, DSL lines, satellite cable coaxes, typically 50 to 100 feet long Ethernet cables. More and more people are putting hardwired Ethernet throughout their house these days, so they got long cables. Long antenna feed lines. All my feed lines are 300 to 400 feet long. So I have to put line chokes along them to make sure I get rid of the induced current in those. Antenna, if you're running an antenna rotator, most people don't know that you have to filter the rotor wires, because they act as a nice long wire receive antenna between your rotor and your radio. Another thing that people should look out for, if you've got a ham shack on the second floor and you've got a ground wire going from your ham shack to a stake in the ground or a cold water pipe, and it happens to be about 16 feet long, you're going to have a lot of problems, particularly on 20 meters, because at 20 meters, 16 feet is a quarter wavelength. So if you know anything about quarter wavelength transmission lines, if it's 0 on one end, which means it's in the ground, it's going to be very high impedance on the other end. So you're sitting here and all your other bands are fine, but on 20 meters, you got hot, your microphones is hot, and it's causing sparks. You got all kinds of issues. It's because your feed line, your ground wire, is the wrong length. So I tell people, make sure it's not a quarter wavelength on any band, and it will make a huge difference. So people call me up and say, hey, I got all my RFI is just fine, but on 20 meters, it's killing me. I'm on the second floor. And so we always have them changed to 21 feet or something that's an oddball number. And that usually solves the problem. You don't need ferrites or any of that kind of stuff. Just make sure you don't have any quarter wave transmission lines for ground wires. On the other hand, if you're getting interference from FM broadcast stations, 20 meters to up to about 450 megahertz, those types of things usually affect short wires, all right? Look for short antennas, speaker wires, and things like that. I'll give you a quick example. I run a lot of power on 6 meters. 6 meters was wide open to Europe from California 3 days ago. It's dead right now. I just checked it before I came in here. But one of the things that I noticed was, of course, I have ferrites on everything. I had it on everything except my speaker wires, all right? And my speaker wires happen to be resonant on 6 meters. So when I put out all that power, all my speaker wires from my radio just went nuts. They were receiving only, and this is only on 6 meters, they received that signal, fed it back into the radio, and caused distortion all over the place. So once I put ferrite filters on the speaker wires, the problem completely went away. All right. The teacher learned the lesson the hard way. But the fact of the matter is, short wires, high frequency, long wires for low frequency RFI. And that's true of transmit or receive. The antenna, so what do these antennas do, so to speak? Well, what they do is they pick up that radiated signal or conducted, could be conducted, they could be hooked directly to it. and it induces a current in them. And that current is what is causing the problem, all right? And if you have multiple wires, generally a radiated signal will have current in all the different wires of a bundle, for example. And that's why it's called common mode current. It's common to all the wires that it hits, right? So if you're transmitting the wires in your bedroom and the wires in your bathroom and the wires in your kitchen are all going to pick up the signal, and it's going to be common to all of them, okay? So the question is how do we reduce that current? That's the whole gist of what ferrites are used for, is reducing that current so that it doesn't cause interference to the thing that's plugged into the other side. All right, so here's just a quick little picture of how that works. Left-hand side, you have a victim receiver. It's got an antenna, which could be an actual antenna. It could also be a DC power line. It could be a USB cable, whatever. And you have a source transmitter on the left-hand side over here. It's transmitting, and that signal hits the wire, and it feeds it right into the receiver. But if you put a little stop sign on it called a choke right here, before it gets into the receiver, it never can get in there, but it passes the normal signal just fine. All right, so it will stop it. And likewise, if you have a source transmitter over here, and this is your radio, for example, and let's say this is a very noisy wall wart. You have a wall wart plugs into the wall, and it acts like a little transmitter, and it uses the wall wiring as its antenna. If you put a little ferrite on before it gets to the wall, it will stop that noise, and therefore, with no antenna, it can't transmit it, and therefore you have a much quieter receiver. All right. Well, the whole basis of how this works, either on transmit or receive, is reducing the current. And here we're going to get into the only formula in the whole presentation. It's called Ohm's law. All right. And so I hope you all remember it. It's E for electromotive force, I for current, R for resistance. So if you take out the I and the current is equal to the voltage divided by the resistance. So theoretically, the higher the resistance, the lower the current, right? That's a real positive statement. So how do you get rid of the current, or how do you make the current low? Well, one thing is you can shut off the transmitter. You turn off the radio and don't transmit anymore. So E is 0. When E is 0, I is 0, okay? The other thing you can do is you can make R relatively large. And I'm going to say relatively large means about at least 1,000 ohms. All right, and I'll show you how to measure that in a second, but it has to be about 1,000 ohms at the frequency that you're interested in. And if it is, there'll be a measurable difference in the current. If it's 100 ohms or 10 ohms, you're not going to see any measurable difference. You can't hear it, you can't see it, and it doesn't do you any good. If you're protecting a victim, let's say a radio, okay, then you need the resistance even higher, typically 5,000 ohms or better. And then you'll see a significant difference. And we'll show you some measurements in a couple slides that show you how to do that. The objective is real simple. We want to minimize that current. That's all we want to do. And we're going to use ferrites to do that and show you how that works. By the way, I have a little trivia question for you. Maybe some of you know this, some of you don't. But Ohm's law has E, I, and R in it. E stands for electromotive force, starts with an E, right? R stands for resistance. Now, why is there an I in it? Shouldn't it be a C for current? What does the I stand for? Now think about that, and I'll ask for an answer a little bit later. But that's a good trivia question. That's a good bar question, by the way. If you're at a bar and talking to a bunch of hams, it's an easy way to get beer. Okay, so let's talk a little bit about ferrites and how to select them, how to buy them, how to configure them, where to put them, and all that kind of stuff. All right, and we're going to show our little ferrite friends down here because they sound very similar to ferrets. Okay, so ferrite topology is another word for shapes. They basically come in 3 different shapes. One is like a slip-on bead, okay, like a long tube, and it's always longer than it is wider. That's why it's called a tube. All right, and that's the one on the left-hand side here. It's called a slip-on bead. There's another one that looks like, kind of like a clamshell. It's got a it's got a hole down the middle, and it shuts tight. It's really useful for cords and things that have big connectors on the ends. You don't have to take the ends off where you have to take them off with the slip-on beads. You have to take the connectors off before they'll go through. With these, you don't. You just put the wire in there, lay it shut, and snap it. The toroid rings, and most of these rings are either 2 to 4 inches wide. They're pretty big. They'll take big plugs in the center. All right, we'll show some examples of how that works. The fuzzy ferrites are not part of the solution here, but a lot of people get that word mixed up with ferrite. So we put them in here just to make sure you're clear. All right, so what are some of the characteristics of these things called ferrites? Ferrites, excuse me. Even I get mixed up at times. They're cheap, they're easy to install, and they suppress, typically, they'll suppress RFI from about 100 kilohertz to 2 gigahertz. That's their comfort range, so to speak. They work on all conductive paths. We're saying that a different way. There has to be a wire in the ferrite somehow for it to allow it to suppress the current. And the conductive path can be an antenna feed line. It could be coax, AC/DC cables, input/output cables, Ethernet cables, you name it. And by the way, you can put more than one type of cable through the same ferrite. Remember, it's common to all the wires, the RFI, right? So you could put an Ethernet cable and a USB cable and a DC power line cable all through the ferrite if it was big enough to take it, right? And it would filter it for all of them while letting the individual signals go through just fine. Okay, they're very effective, but you have to understand how they work and how to choose them and where to install them. And that's what we're going to go through next. Remember, all we're trying to do is reduce that current. So let's talk about a fancy graph here. Now, I'm just going to start off by saying ferrites are just like resistors, but they're frequency dependent resistors. That is to say, they have different frequency. At different frequencies, they have different resistance. So unlike a normal resistor that you would put in like an electrical circuit, the old carbon resistors, for example, they're pretty constant. If you had a 1,000 ohm resistor, it's constant from DC probably up to maybe 100 megahertz. And then it might become inductive or whatever. But ferrites don't work like that. Ferrites, their characteristic is not flat like a mesa, like a normal resistor. They're more like a Matterhorn. Okay, they peak at some particular frequency range, and they're very good at that range. But outside the range, they're not really that good at all. So, depending upon the composition of a ferrite, all right, we'll talk about that in a second. You have to choose the correct ferrite to have the resistance at the frequency of the interference. All right, the fundamental frequency of the interference, right? Not the harmonic. Okay, so this graph here shows, if you can visualize this, there's a graph and it looks, it's got on the sides, it goes down quite a bit, and then it's got a peak right at the center, and then it goes down again on the other frequency. But the frequency of interest is right about between these 2 points. It's about 80 to 300 megahertz. This is a super resistor. It's really good at those frequencies. So you would use this type of ferrite if you had interference on a 2-meter repeater, for example. All right, it could take away a lot of the cohabitation interference from other repeaters that may be in the same building. All right, so ferrites are characterized by the resistance that they have at a certain frequency. All right. Okay. And they have to be used in that particular region. So how do you increase the resistance on a ferrite? All right. So we're going to talk a little bit about that now. Now, if you remember resistors, they add in series. So if you put a 100 ohm resistor next to another 100 ohm resistor and connect it to another one, you would get 300 ohms. They add in series, right? They divide if you put them in parallel, but they add in series. Well, ferrites are exactly the same way. You put, if an individual bead had a impedance of, let's say, 80 ohms at a particular frequency, you put 2 of them in a row on a cable, they would have twice that. Three of them would have 3 times that. So we have a little graph here of 5, 10, and 15 bead ferrite filters, right? In this case, they're just line chokes. There's a picture of them on the right-hand side here. These are just put on coax cable, for example, 5, 10, or 15 beads, and they're used at HF. In this case, I think 40 meters is what we're measuring them at. So 5 beads has got 400 ohms, 10 beads has got 1,000, 15's got 1,600 ohms. But what's interesting is that the beads will keep increasing up to a certain threshold frequency, and that, which is about 30, 31, 32 megahertz in this case. But above that, 5, 10, or 15 are exactly the same. All right, they're getting outside their range of effectiveness. Right, so if you have a problem on 6 meters, there's no sense putting 15 beads on it when 5 beads will accomplish the same thing. Right, so you kind of have to know what the characteristics of it are. We've already figured all this stuff out. I'm just giving you the theory so that you'll be a little bit up on what this is all about. So you can always put these in series, and this is true for clamp-ons and it's true for the slip-ons. Both are the same, and rings are also identical. But rings and other ferrites have one additional characteristic, which is really important. It will save you a lot of money if you're going to be using these things. And that is, a ferrite resistor has got an inductive component to it. All right, an inductive component means that the resistance increases as the square of the number of turns. All right, let me say that a different way. If I have 1 turn, I get a resistance of 100 ohms. And if I loop that wire through a little bit bigger hole and I have 2 turns through it, I get 4 times the resistance. It's 2 squared. If I put that wire through 3 times, I get 9 times the resistance. So for a little bit of extra labor and a little bit bigger hole, I've got the same as 9 in a row for maybe an extra $1 worth of ferrite than I would if I had to pay for 9 of the ones in series. All right, and that's a very, very useful characteristic. So you can put, actually you can take a ferrite, put 3 turns through it, and then put another one next to it with 3 turns through it. It'll double, but it won't be 9 times like the first one. You see, so here's an example at the bottom of the slide where I have 1 turn and it's about 100 ohms at 40 meters. And if I take that same one, I take a little bit bigger ferrite with a little bit bigger hole in it, and I put 3 turns through it, I measure that about 900 ohms. It's three squared. And if I put an AC cable or I put a big ring and I put 7 turns through it, now I'm up to 6,400 ohms. And now you can see how by getting a larger ferrite with a bigger hole and putting more turns through it, you can get to those 1,000, 5,000 ohm numbers that I've been talking about, where you have significant difference in noise levels and significant difference in radio frequency interference on your cables and stuff. Okay, so there's one more item on ferrites that you have to know. Not only do they increase in series, they increase to the square of the number of turns, but if you change the material that's in a ferrite, because they're not all born the same, they're born differently, they have different compositions, and the different compositions are done so that there's different frequency ranges for the different ferrites. And we conveniently call those frequency ranges or compositions mixes. All right, and you may have seen an article or heard about an article in the ARRL. They use what they call mix 31, which is a very common mix for suppressing RFI and typically the 1 to 300 megahertz range. All right, and really it's good from about 4 to 5 megahertz up to about 500 megahertz, but they spec at 1 to 300. However, if you got a switching power supply and it's causing noise at 200 kilohertz, mix 31 is useless. It doesn't do you any good because there's no resistance there. So they came out with, probably about 10 years ago, they came out with something called mix 75. And mix 75, on this little graph here, this shows you the high ports of all the different mixes. Mix 75 right in the middle of the broadcast band, so it's great for broadcast interference. Mix 31 is probably the best other overall one. And then we have mix 61, which is here at the UHF, VHF. Then you have 43 and 46 in here. So those are the typical ones that you hear about and you read about in all the different articles. and that are talked about all the time. The most useful ones from my standpoint is the 75s and the for low frequency, and also the mix 31s. Unfortunately, each one of those is not made in all the different shapes and sizes. They only made certain ones. And so a mix 43, which has been out since, it seems like the 1950s, is made in every size and shape in the world. And it's a close second. And sometimes you have to use it because it's the only shape that'll fit a really large cable or something like that. Okay, so now we know that there are certain compositions, and different compositions have different frequency ranges. All right, so there's one more thing you need to know, and that is, how do you buy these things? Where do you get them? How do you buy them? All right. But first of all, I'm going to tell you how not to buy them. All right, because people fall into this trap all the time. They get on Amazon, they get on eBay, and they'll see an ad similar to the one on the left-hand side over here. It says, buy a pack of 20 of these, no tax, free shipping, $19.95. All right, looks great. They're the right shapes, right forms, multiple sizes, et cetera, et cetera. There's only a couple major problems. They don't tell you what the mix is, so you don't know what the frequency range is. They don't tell you what the resistance is, all right? And there's no mix designation. So it's like buying a resistor without the color codes on it. You have no idea what it's going to do. It's just cheap, okay? All right. And I'll tell you from a practical standpoint, most of these types of ferrites, where they don't have any designations on them, were actually old video cables that have been sent over to China, and they burn off all of the outsides of them, and they put new cases on them, and then they send them back, or they sell them directly from China or through eBay. All right. And unfortunately, if it's a video cable, the video cable range is typically 300 megahertz to about 800 megahertz. So you try using some of these cheap ferrites on your HF station, which is 30 megahertz or below, you're just wasting your money. They will not work at all. Right. So don't get stuck into buying something that's without specs on it. The other thing that you'll find is you go to a swap meet, and there's guys with boxes of these things that say, take, 10 cents a piece, 20 cents, $1, whatever. Problem is, again, there's no specs. And you know what, if you take a ferrite, right? If you take a ferrite, here's a ferrite ring, for example, let me get it in the right place here. That ferrite ring looks identical no matter what the mix is. It's very, very similar. So unless you have a real trained eye, you won't know what the frequency range is. I can tell because I've just been dealing with it for such a long time. But for the most part, consumers, even hams, just don't know what they are. And so you're going to be buying the wrong thing, and it won't work. You'll become a non-believer very quickly. So what's the alternative? Okay, well, first sales pitch of the night, right? No, but this is true of anybody that you buy ferrites from. You want to know what the mix is. The mix will tell you the frequency range. In this case, there are 1/2-inch holes in them. That's why they're called 1/2-inch. There's 10 in this package. And for every 5 megahertz, 5, 10, 50, 2500, 250 megahertz, this is the number of ohms for one turn through the center. All right. So if you wanted 500 ohms or 1,000 ohms minimum, you could take a small cable and the 1/2-inch hole, you could put it through 3 or 4 times, and you would multiply this number by either 4 or 9 or 16, and you'd be home free. All right. What's a practical example? Let's say you have a 2-meter J pole, right? 2 meters is 144 megahertz, right? You need at least 500 ohms, and 1,000 would be better. But even if you had just a couple of these, you could take at 150 megahertz, it looks like it's about 260 ohms per bead, all right? Just take 2 of them and put them in a row, you're at 520 ohms, which would be plenty for that frequency. That's all you would need, right? You don't need 5, you don't need 10 or whatever. However, if you're doing the same thing with an 80-meter antenna and you still need at least 500 ohms, you're going to need at least 7 of them because at that frequency, it's typically 50 to 70 ohms. You need 7 to 10 to have the exact same resistance to get rid of that current. Okay, so let's do a little recap here and move this on. Ferrite recap is you want to determine the interfering frequency, choose the right mix, the one that'll work at that particular frequency. Choose the size that'll fit the cable, install it on the path, and then retest, make sure it's actually working, and then consider additional ferrites or paths if RFI persists. I'll tell you that if you have an electronic device with 5 different wires going into it, and you put ferrites on 2 of them, it's like putting stop signs on two of all the roads going into a circle. The RFI will come in the other 3. Okay, in other words, it'll avoid the stop signs, it'll come in the other ones, and you'll still have that problem. So you have to do all of the wires coming into a particular radio, or at least take all the wires and put them through one or at least one ferrite. They can all go through the same one, that's okay. All right. I'm going to move on to a little bit of transmit RFI here and talk a little bit about solution kits. How do you just buy these things, put them on, and make them work, for example? All right. So install transceiver and linear amplifier RFI kits. You guys have been talking about different amplifiers and radios and things like that. And the whole goal is making sure that you're not putting out RF or taking in RFI from different lines of your radios and amplifiers. So you want to choke all the cables coming in and out of the radio. You just have to do them all. You can't do half of them. That won't work. All the feed lines or rotor cables, AC DC lines, including wall warts that are feeding audio filters and that type of stuff. If you have a computer, a lot of times the computer has noisy power supplies in it, and they'll feed into the radio. We'll show you some specific examples, but basically every wire coming in and out needs something. Here's an example on the next page. This is an ICOM 7300 current radio, very popular. And you'll see here, we have a ring on the DC cable with 5 turns through it. And we have the cable over here going through the receive transmit cable, coax cable, has 5 turns through a ring right here. And then we also have 3 other cables that are used for interfacing and the amplifier, push to talk, for example. And they have 2 turns through them. All right. So that's the same as having 4 in a row. So this is what we call our standard transceiver kit for a radio that's got 1 antenna. And you buy this, it's $40. It's not very expensive. And we sell hundreds of these every month for all different types of radios. These are good for HF. We also have a VHF one. If you want to get just a little bit better and decrease your noise, you would use a box here, and it's got different filters in it. Again, they're all ferrite, no power required, and that would replace the ring that you have here, and it gives you a big reduction in noise, up to 6 to 8 S units. And that's a lot. Okay, linear amplifiers. Here's an example of linear amplifiers. Meritron 811H. You use the Palomar 400. You put a big clamp on with a 1-inch hole. You do it with the RF out. You do it with the AC line, the relay choke, and also the RF input. Goes through its own ring. This is an example of a Heathkit SB220. Solid state amps are identical. They just they may have a separate power supply, but that's about the only difference. All right, one thing that you should know also is all about coax lines. Any coax fed antenna needs a choke at the feed point. And the reason for that is you don't want your dipole to become a tripole. You don't want your vertical to become a dipole. Why is that? I think most of you probably know at this stage of being a ham that coax has got 3 conductors to it. All right. There's the inside conductor, and then there's the braid. And the braid, even though it's one piece of metal, there's actually a separate electrical conductor inside versus the current that goes on the outside. So as you're forcing a current up through the inside, it's got a decision to make. It's got a fork in the road. It says, do I go back this way or do I stay on the antenna? Well, if you put a big stop sign here called a choke, it says you can't come this way because it's a high resistance. That means that all the transmit signal will stay on the antenna, and that's what you want. If you don't put one there, what happens is you get current coming back down, and that usually is closer to devices in your home, and it causes interference, you see? And so it's a real real advantage. This is an example of a typical coax fed system. We're going to put a choke out here. This is a 3 kW choke. It's actually the best choke in the industry, the best specs. And you would put it right at the antenna feed point. On the other hand, and that will prevent the coax from radiating, right? On the other hand, if you're receiving versus transmitting, and you have noise sources out here, they will actually jump on that outside part of the coax, and they'll feed themselves right into your radio, and you'll get a high noise floor. So you put a choke down here, we call them coax noise filters. It's very high impedance, and what they'll do is they'll stop that noise source from getting into your radio. Very, very useful. And we sell hundreds of these a month just for that purpose, just for quieting down your radio. And I'll show you quickly how to determine whether it's going to work for you or not. Here's the characteristic curves. Again, they're nice and flat. They're not little Matterhorns. They're nice and flat over a long frequency range. This is our little coax noise filter. This is our 3 kW choke, and it's got a static bleeder in here too. I don't know if anybody you knew Art Bell or listened to Art Bell on the radio, but he's the guy that taught me how to do this before he passed away. He used to have two 1,700-foot loops 70 feet up in the air, and he would get wind static of about 90 volts just from the wind, and that would blow out the front end of his radios. And so we designed a bleeder that bleeds off the center conductor continuously to ground, so he didn't have that problem. Anyway, he's the guy that taught me how to do this. And so you want a choke that's very wide band, okay? You look at some of the MFJ chokes, some of the other chokes on the market, they're very narrow band. They'll go up and they'll be very high at one particular frequency, and that's it. If you look at these graphs a little bit differently, and you measure them as common mode rejection in dB, it's easier to see that this particular box here is 38 dB. And if there's 6 S units, or 6 dB per S unit, that's about a 6 S unit noise reduction. Now that's a lot. This choke over here, it's 49 dB. All right, that's almost what 7, 8 S units of noise reduction just by putting that choke next to the radio. All right. Also, likewise, you put it at the coax feed point. Make sure all your energy stays on the antenna. You can make some of these chokes by yourself. And we take one of these little rings out, mix 31 rings. This is an example on a dipole antenna, and it has 5 turns on it, and it provides right around 20, 25 dB of attenuation. If you put more turns on it, you can get up to about 30 dB of attenuation. Again, that's still 5 S units. That's pretty good. All right. If you want to, you can also put multiple beads. Sometimes your cable is so large, you can't put multiple turns in it. So what you have to do is you have to put them in series like this. And snap-ons and slip-ons are all pretty much identical for characteristics. So here's an example from 1 to 6 meters, 1 megahertz to 60 megahertz. There's 5 beads, 10 beads, and 15 beads. The more beads you put on, the higher the resistance, the better the suppression. All right. If you're using, if you want to do low frequency stuff, remember one of these mixes is 75, really good at low frequencies. The mix 31 starts right around 80 meters, and it's much better out here than these. And so you have to know where the interference is. By the way, you always filter the fundamental frequency, not the harmonics. Right. So if you have a problem with you're next to an AM broadcast station, for example, on 1200 kilohertz, but you're hearing something at 3600 on 80 meters, it's probably the third harmonic of that 1200. You put a filter in for 1200, not for 3600. It'll be a completely different ferrite, but it gets rid of all the harmonics in addition to the fundamental. You can also install specific kits, all right, get rid of this problem here. And some of the, actually, this is a nice little joke. This is what your neighbor wants to do. He wants to just choke you, and instead of you choking your electronics. That's their strategy. And it's a beautiful kitty, by the way, Margaret.
Thank you.
the ham solution to the neighbor's RFI, let's say your neighbor's causing a problem. You rolled that big long wire out the window and the neighbors are having problems with their TVs or whatever. You have to determine, is it you causing the problem? In that case, it probably would be. But in a lot of cases, it's not even you. You may not even be home. The transmitter may not even be on. You may be watching TV and they call up and say, hey, turn off your radio. And so you have to decide whether it's you or something else. Determine the frequency of the transmitter that's causing the issue. And like I say, it may not be you. Find the path to the victim, choose the RFI choke, and then put it in, install it. Now I'll tell you, most of consumer problems with neighbors is because you're transmitting on either 80 or 40 meters, or 160 is even worse, because it's their AC power lines that are picking it up. They're acting as antennas, and it's affecting the devices plugged into them. You generally don't have much interference on 20 meters or 10 meters or 15 or 17, the high bands, because unless they have real short resonant wires in their electronics, they won't see it. Right? Generally, it's because their AC power lines are picking up your signal. So we have multiple RFI kits for computer RFI, for routers, laptops, desktops, you name it. Garage doors we talked about, home theater systems, alarm systems, miscellaneous RFI. This is the general solution. If you got a neighbor that's got problems, generally you buy 10 of these things in a kit and you start installing them on, you have them install. Think about it. You have them do the installations on their own stuff. If you start doing installations on their equipment, it will never stop. There'll always be another problem and they'll always think you're the problem. And so if you have to, buy it for them or tell them to come to the website and we'll walk them through how they do it. Okay, a little bit of recap. Again, you got to find the source and the path and install the choke, put chokes on all your antenna coax lines, and consider additional filters if you need it, or if you just call us, we'll tell you what the specific problem is and what the solution is. All right, I'm going to finish off with receiver noise. I'll tell you a quick little test here to install a coax noise filter. It's again the same problem, but typically received noise is usually coming in from a wall wart, or it's coming in off the coax line, or it's a switching power supply. Those are the most common. And here's a real easy test that you can do. On your radio, if you have a high noise level, just unplug the antenna altogether and see if the noise level goes away. If it goes away 100%, then you know it's coming in through that wire. If it doesn't go away, it goes from an S7, for example, down to an S3 or something. You know there's another wire plugged in there, and it may be your DC power supply, it may be the USB interface to your computer or something like that. So just start unplugging wires until the noise goes away without turning the radio off, obviously. Okay, in most cases, people will find that when they take the antenna away, the noise goes away. Right, because the antenna is big, it's a big piece of wire, it's picking up noise. But remember, there's two receive antennas here. So the first test is you unscrew the back of the coax connector, unscrew the back here, and you just put in the center pin only and measure the noise level. It could be S1, S2, doesn't make any difference what it is, relative, right? And then screw in the outside and see if it changes, see if it goes up. If it goes up, Ferrite filters, coax noise filters, all the stuff I've been talking about will get rid of that difference. It will not get rid of the bass, the S1 or S2. But in a lot of cases, in particular if you're using antenna switches, you'll find that this will go up 2 to 3 S units. And you can't even hear the person that's underneath the signal. You put the coax noise filter on there, or a Ferrite filter, and bingo, the guy pops right out. And now you hear him. Right? It's a real simple test. Everybody can do that. If there is no difference, then all the filters in the world aren't going to do you any good. The only thing you can do is either get rid of the noise source or move your antenna away from it. That's about all you can do to lower the noise. Again, same principle here. You put the coax noise filter closest to the radio, and that gets rid of all these sources that are jumping on the outside of the braid and going into the radio. This stops that current by putting a high resistance in the braid so that it doesn't pass the current. Therefore, you don't get the noise. If you have a sophisticated system, you would put and you have multiple antennas, you would put your chokes at the antenna feed points. And you would also put another noise filter out here prior to the antenna switch. And then you go to the tuner, the linear amplifier, and put another noise filter here before you get to the radio. All right. I'm just going to give you a little quick heads up on antenna switches. If you have an antenna switch, in this case, we have 2 antennas, but remember, you're only switching the center conductors. All the outsides are still connected. So if you had in this particular case with 2 antennas, you actually at any one time have one braid in the center and you have another braid. You'll have 3 antennas always connected to your radio. If you've got a switch with 4 antenna switches on it, 4 antennas hooked to it, you always have 5 antennas. So you may not even be using that antenna, but the noise is coming in off the braid of the coax and it's connecting in your antenna switch. And that's what's getting into your radio. Very subtle, but major problem if you've got an antenna switch like that. So the solution is you put the little chokes, the coax noise filters, before you do the switching, not in the common line. I mean, the worst case is you could put it in the common line, but that means all the braids are they're still adding up all together, and you have to filter them all out. Here, you're only every one is individual. So when you do your switching, you have 1 antenna, 1 braid. That's it. All right. If you're in a multiple transmitting situation, or you're in a contest station, or even if you have a switch with, I have switches with 8 different antennas on them, and every one of them has got one of these big chokes here before it even gets to the switch. And then every one of my radios, and I have like 5 radios down here, every one of these has got one of those on it before it goes to the switch that goes into the linear amplifier. You have to do that, otherwise the noise just follows right through, no matter what the grounding is and everything else. You've got noise loops coming in on the coax like that. Okay, here's some comparisons. You can do a simple choke like this. I think somebody asked that question. You can do multiple turns. Multiple turns is always better, or you can do the little box. The little box gives you 3 to 6 S units. Multiple turns here gives you 2 to 4 S units. You get 1 to 2 S units here. Sometimes you have to do these because you got big cable, but you could also take this big cable and plug it into this box, and you could get 3 to 6 S units rather than 1 to 2. So different ways to do it, and different ways. We also make them all the way up to 10,000 watts, and they're all essentially the same specs. They always go up to 6 meters. You can take the rings. The rings come in different sizes. Put them on your AC/DC power supplies. Here's one for an AC cord. Here's one for a large generator. Right? Large generators have big cables on them. We can put 2 in series like this, right? For these 240 volt cables. Right? Just some different ideas. If you have a switch mode power supply, you got to do the input and you got to do the output. These act as little transmitters. They're transmitting noise this direction on top of the 12 volts, and they're transmitting noise out this way into the AC power lines. It's low frequency. You got long antennas. They love it. It's perfect for them. All right. So a simple little 2 mix, in this case, mix 75 filters, because they're low frequency, solves that problem. Everybody's got wall warts all over the place in your house, probably. You got to put a little filter on there. These are really cheap. You buy them in 5 and 10 packs for like 20 bucks. And you put them right on the where the device is, and they'll stop the noise that's coming out of the devices. If you've never used this stuff before, we have all different types of combo packs and rings and those types of things. Take a look at the website, and if you so desire and you want to check out, use the discount code called newbie. You're a newbie, you ever used these before, and you get a 10% discount. And that's good towards the end, all the way to the end of the year. So basically, the way we price things is you buy 9 to get 1 free, and they're all packed in a box and they're safe. And we have very little breakage, but lots of great success stories. All right, I'm going to give you a quick three questions here, a little test. To see if you've been paying attention, I'll go through them and give you the answers. What are the two best ways to increase the choking resistance of a ferrite filter? Want to use high resistance wire and multiple turns on a bead. Maybe that'll work, but you're going to get a lot of loss in the wire. Use multiple turns and double shield coax. Okay, double shield, triple shield, quadruple shield coax has zero effect on RFI, because the outside of the second or the third or the fourth still acts as a separate conductor, no matter what. Doesn't make any difference how many you got in there. The shields only protect the signal in the middle from getting out, but it still will reverse itself at the end of and come down the outside. Use multiple beads in series with multiple turns. Yeah, that could work. Use mix 31 and mix 75 beads in series with a single turn. Well, the best answer to this is number C. All right, is use multiple beads in series and multiple turns. And in the case of some of our chokes, we actually use multiple mixes so that we get a nice broad spectrum also. Mix 61 is used in which frequency range to suppress RFI common mode current? 1 to 300, 200. Obviously, that's one of these. It's not the CB band, but I'll tell you, CB guys buy a lot of filters from us. It's very popular, and they run a lot of power too. I've had CB guys call me, and they're running 2-inch cable, 30,000 watts out of Puerto Rico or some of these other countries and stuff. It's amazing. But we have filters for them all. Anyway, the appropriate answer in this case is mix 61. It's 200 to 2 gigahertz. All right, here's what's one of the best kept secrets in ham radio. What's one of the best kept secrets in ham radio? Ladder line is more lost than coax. That's a negative statement. That's not true. Ladder line is great for antennas. It just doesn't work in the rain. A coax wound choke. I didn't tell you about these, but a lot of times you'll see in the magazine articles where they take a big piece of PVC and they wind coax around it and they say that's a choke. All right. Well, it's a choke in the sense that it's a tune choke. You have 28 to 30 picofarads per foot of capacitance, and you got so much inductance because of the diameter and the number of turns, but it's only good at one frequency. It's not broadband. So if you had a 40-meter vertical and you had a tuned 40-meter choke on it, it'd be fine. It's cheap. It's easy to do. All right. But if you want a filter that works on a whole bunch of bands, you have a tri-bander, for example, or you have an off-center fed that works 6 different bands, you need something that's a little bit broad. And so coax wound chokes are basically useless unless you have a 1-band antenna. All ferrites work on all frequencies, so buy the cheapest. That's the Amazon answer, right? It's wrong. Coax noise filters reduce common mode noise level in your receiver so you can hear more stations. All right. That's the true statement. That is the one. But the next one's pretty good too. I hope it's true. All extra class hams go to heaven. One more bonus question, then we'll get back to Q&A for you guys, and I'll tell you what the I stands for also. Which company is your best source for RFI solutions? You all should get this right. That's our website. That's our phone number. That's who I am. And the presentation is available on the website. And it's also all over YouTube too. People record these, put them up on YouTube, put them up on all our different websites. So I keep changing the slides every now and then just to make it interesting, but that's generally, it's available just about everywhere you want to go. And I'm glad to do these. They're fun to do for me, and I enjoy it. So I'm going to unshare my screen and then open it back up to Margaret and the kitty. Anyway, I'm all yours. If you got questions, I'll be glad to answer.
Got one, Bob. When you're choosing the size of the ferrite, say either it be a tube or a clamshell, how critical is the diameter as opposed to the diameter of the wire? Does it need to be tight? Just need to touch one side? How critical is that?
Okay, that's a great question. And the answer is it doesn't make any difference. It's all about the length of the ferrite is most important. So you can put multiple wires in there. You can put it so it's real snug, or you can put so it's got some wiggle room in there. All right. And it won't make any difference because it's the length of the ferrite along the cable that's actually doing the work. It's not whether it's real snug or not snug. Did that answer your question?
Yes, it did. Thank you. Anybody got an answer for the eye?
Comes from the French.
Okay, keep going.
You said
Ready for
you're
the-
close, Angelo. Now finish.
It stands for
Impulse de co-
intensity.
Oh,
Intensity is what it stands for. It's a great bar question. I always win a beer on that one, but it stands for intensity. It's the acceleration of the current going through it, and they called it intensity in those days, not current.
makes sense.
So now you know. There's got to be some more questions, and this RFI is a complex issue. It affects
It
all
is,
of us
but-
all the time.
You did such a great job explaining everything that
Well, thank you for that.
So I have a question about the, again, putting chokes on. You say they could be a little bit loose now. Is it okay to put, would you say, something around the wire to make sure that the choke is tight?
No, you can put multiple wires through the same. Let's say you have a 1/2 inch hole and you got a 3/8 inch piece of wire, you got an Ethernet cable or something like that. Just put it through there. If you want it, if it's vertical, for example, it's going to slip all over the place because it doesn't fit, right? So you can put a nylon tie or something like that to make sure it doesn't move, all right, if you want to keep it in a certain place. But it's the length, it's the 1.5 or 2 inches or however long the ferrite is that's doing the job. It's not whether it's snug or not, all right? So if you can, always get a ferrite with a hole that's a little bit bigger than the cable you have and put more than one turn through it. You know, put 2 turns through it. It's the same as buying 4 in a row. Whenever you do that, it's much more economical to do it that way. So if you have 1/4 inch cables, buy 1/2 inch ferrites, you know, that way you put 2 turns through each one.
I have a question, Bob K1BZ. And
Go
I'm
ahead.
not sure,
Oh, go
not sure where Shay is, but if you have a lot of different wall warts around your house, should you just go through and put chokes on all of them? Because I mean, your power lines are going to pick up any radiating interference. Or
Yeah,
should you go and try to find the ones that are the defending noisemakers?
Well, if you have a lot of them that are together,
Yeah.
put them in a power strip, and then put one of those big rings, those mix 75 rings on the line that plugs into the wall. So that one stops all the ones that are plugged into the power strip. But sometimes those wall warts create noise in the DC lines that are coming out.
Exactly, they pick
And
it
that's
up.
where you need to put an individual ferrite ring on every one of them going into the devices. The answer to that is yes, but the problem is on the other end is now it's transmitting on both sides, right? It's going on the
Right.
AC side and the DC side. So you want to be able to isolate the AC side, and the way you do that is plugging them into a power strip or an extension cord or something that you can wrap a ring on before you plug it into the wall.
Well, yeah, see, I've been getting rid of those and just having a box that has a number of like 6 outlets in it and just
Yeah.
plugging that.
Yeah, you can do it that way too. Yeah. These days they're all converting to USB ports, it seems like.
Exactly.
And so you can use a USB port that's got, one in and 6 outs, for example. And the fancier ones even got on and offs on each one of them. So you just unplug and just hit the little switch.
Thank you.
Sure. You still need ferrites on those, but it's a lot cheaper.
Yeah.
to do it.
This is Steve, WB2KTV. Are you saying that you would put one of these ferrites on the front end or on each of the back ends coming out of one of those multis. Because a lot of us here are all using these USB wall wart type powered micro power UHF and VHF showery nodes and clear nodes and whatnot. And they all have the same darn problem, and that is they all hum like crazy. And we're all doing everything we can think of to get rid of that hum. And we totally understand the theory behind it, but the question is where to put the choke in the feed line going into the Raspberry Pi that runs the radio, on the antenna side, on the front side where the AC power goes into the wall wart. Exactly where's the best place for those?
Well, you can always use the shotgun approach because
Okay.
it depends upon, in the end, it's a facetious answer, I know, but it depends on what's creating the noise. All right. Is it the little Raspberry Pi creating the noise? Is it the power supply for the Raspberry Pi that's creating the noise? Or is it because it's the Raspberry Pi and the coax cable that's using it as a transmission line causing it? So you basically, you can take a box of ferrites and just start putting them on different ones until the noise goes away. And then, aha, it's that line, it's that particular line. So
Yeah.
and it's hard to say what it is, because it could be any of them, you see. And so the only way to really solve that problem is start putting them on and measure the results as you do it.
Yeah, the other problem with that, of course, is a lot of these feed lines, the line from the either the wall or the power strip to the wall wart is short. The line from the wall wart to the Raspberry Pi is short, and you run out of line really, really fast.
Yeah, it takes at least 3 or 4 inches on the small rings. The rings are only about an inch wide, but if you can put 3 or 4 turns through it, that may do wonders for knocking down some of the noise. You don't have to put 10, 15 turns. That's obviously better, but you use what you got, and if you have to, you make a little extension to it. If that particular line is the issue.
Okay, thanks.
Good luck with that, because that's not an easy problem to solve, but it's solvable. Any other questions? You're an easy group tonight. What's your cat's name, Margaret? You gotta unmute yourself.
Shay,
Shay.
SHAE.
Oh, very nice. Very cute.
He's well known in the blind hams community because he's got a bell on his collar.
Oh, what a cutie pie.
So when I'm on the air with the guys, they can hear him running around.
Oh, it's really cute. We raised Maine Coon cats for a long time. Yeah.
Oh, so you think he's got some Maine Coon? I was wondering about that.
In his ears, he does. It looks like the way his ears are fluffy.
Well, if he's got noise, you put a ferrite
Put a ferrite bell on him.
Yeah, and also the tail.
Oh yeah, very nice fluffy tail.
Fluffy tail.
Yep. Yeah, he's got some Maine Coon in there.
Maine Coon, yeah. I was wondering about that. I was thinking he probably did.
Yeah, his eyebrows are right below his ears. You can tell that's a Maine Coon thing.
Oh, okay. I didn't.
Yep.
Know that.
Yeah, we've had them for a long time. We actually went to Maine to get ours. And
oh wow.
My wife's sister runs a Maine Coon cattery and had lots of them there. So we flew back there and got a couple that didn't want to have babies anymore. So we just took those and had them for many years. Really nice cats. Very well tempered.
Oh, yeah, I got this one from a coworker's friend.
Yeah, beautiful kitty. Beautiful cat.
Thank you.
Well,
Any other questions, RFI or otherwise? I've been a ham for a long time. I know a lot of stuff. So if you want to pick my brain, you're welcome to. Otherwise, it's time for me to go get some dinner.
Well,
I'll
I
have
got one.
to share this with friend of
ahead.
mine, he just moved to Maryland,
Yep.
and all his neighbors are running these solar panels, but they're not using the solar panels with the battery. They're just getting the pure electricity out. He said
Yep.
he can't even turn his radio on anymore.
Yeah. Problem is that they're, all the new ones, they're not using single inverters anymore. They're putting micro inverters on every one of the panels. And so if you think, and they all have IP addresses, they're all separate, addressable, individual monitoring, all that garbage. And as a result, they're all in this huge loop antenna with multiple transmitters feeding the loop, you see. I mean, they'd be much better off if they even twisted the wires, but they don't when they put them in. And there's not a whole heck of a lot you can do. I've worked with a couple of solar companies here in the West Coast who actually buy from me, and I refer them hams if they buy my kits to put in, so that the hams can actually work their radio. But if it's already installed, boy, you're SOL in terms of doing something. You got to do portable operations or something else. Most people won't change their or uninstall and reinstall and put the ferrites on there. If you put ferrites on every one of the inputs and outputs of every one of the little micro inverters, it solves the problem. But most people aren't willing to do that.
Most systems have
Oh.
20, 30 solar panels on them. So
Yeah,
that's-
yeah, they do.
That's why they don't want to do it.
Yeah, it's expensive to do it. I have
Bob,
friends-
sorry.
No, go
I
ahead.
have two questions. One is, can we get a copy of the slides?
Yeah, they're on the website.
Oh, okay. And the second question is there any interference from any of the various cable companies in the United States? Like the cable in your house and the boxes and.
Well, yeah, the boxes can be a problem. Sometimes it's the power supplies. I know Rokus are a problem sometimes too. The old Rokus, the new ones are better, but the old ones, the box itself and the power supply going in that box was an issue. Some of the older satellite boxes can be a problem, but they're also a problem if you're using satellite, because again, you get their coax fed, right? So you transmit, and guess what goes on the outside of that coax into the satellite box? It's your signal. So we actually make those little black boxes that I was talking to you about with F connectors on them, so that you can put them in the satellite feed boxes before they go to the cable, before they go to the satellite box. And that solves that problem. But as far as them interfering with you, usually it has to do with the power supplies for them, not because they're radiating something themselves. Most of the cable and the TV issues with satellites and stuff are because hams are interfering with them, not vice versa. But I have troubleshooted some power supply issues with various different ones, and they're all guilty in terms of brand, but usually it's power supply related.
Thank you.
Was that both questions or one?
Yeah, no, that was it.
Okay.
I'm done.
I got a question about the antenna I just bought. I asked you about running it as a vertical. It's a 97-foot 9-to-1.
Yep.
And I was asked about running it as a total vertical, and you said it might be better to run it as an inverted L. On a 97-foot, what would be the optimum height for the vertical and for the horizontal portion of that antenna?
Well, with a 97-foot, generally percentage wise, typically it's 30-70, 30% up and 70% out. But if you can go higher, that's even better. I mean, if you could do total vertical, that would be all right, or total horizontal, that's fine too. You just got to make sure you got enough coax between. See, 97 feet takes about, the choke's got to be at roughly 40, 45 feet or something like that. So the total antenna is 97 plus 45. So the choke's got to be at about the 45-foot level of the coax. And because they both radiate. So if you had a completely horizontal and you had 45 feet of coax with a choke on it, you'd probably have a really nice antenna.
I've got the counterpoise kit with mine. Do I need to still have the 45?
Yeah,
feet
you
of
still
coax?
need that. Yeah, the counterpoise kit is primarily for people who do summits on the air, national parks on the air, and they can only get the antenna up 8 or 10 feet or maybe over a tree branch and then go out. And so they have very small horizontal, very small vertical. They typically run inverted L's. They throw them over a branch and then they take them out to a cyclone fence or something. And so they need some kind of additional counterpoise. They still need the choke, but they need some additional counterpoise for certain bands. And so the little counterpoise kit is used for that. But if you're running it all horizontal and you have a long vertical coax, you can't put the horizontal, you can't put the counterpoise kit on, won't do you any good because they'll be hanging in the air. And so it's primarily used for people who are using inverted L's and who are doing a lot of portable operations. And you can put multiple counterpoises on, by the way. You may have a counterpoise using your coax at 45 feet, but the 30-meter band doesn't come in the way you want to. So you can put another parallel one off of the side terminal of the 9-to-1. And that's a little shorter, for example, and that may bring in 30 meters just fine. So I've seen people with multiple lengths of counterpoises depending upon specific installations. Now we have people that run these around the eaves of their houses. They put them in the attics. I mean, there's almost 10,000 of them out there. So it's yeah, they're very friendly antennas. They work a lot of bands for the length of the antenna, and there's lots of different types of configurations with multiple counterpoises. Essentially, they're off-center fed antennas with a wire portion and a counterpoise. And the counterpoises can be in parallel to work different bands. But generally, all you need is one for most of the bands if you have a 3-to-1 tuner in your radio.
Okay, well, and now what's an optimal height off the ground should the 9-to-1 be, or does it matter?
It doesn't make any difference. Usually you want them a couple feet off the ground so that, kids and dogs and kitties can't get into them. But it's unlike the end-fed half waves, which have 1,000 volts on them. That's why I don't sell those. The voltage is too high. But with these, you just want to kind of keep them out of the way of pests, so to speak, who could get into it. And 2 feet, I run most of mine at 2 feet, 3 feet. At all the Hamfests and stuff where we demonstrate these things, we have a 20-foot fiberglass pole, and we run it up there, run the counterpoises out, and then run to a cyclone fence or a wall or something, and that seems to work just fine. So
I can't wait to get moved so I can get it up in the air.
the higher you can get it, the better, because
I
the
got some
current on
130
these is at the feed point.
I got some 130-foot old growth oak trees.
Oh yeah, there you go. Well, just shoot it all the way up, or run the coax up and then run it out.
That's right. Anybody else?
I have one question.
You only
For
get
those
one.
that run the antenna around the eaves of their house, well,
Yes.
if you have metal, your eaves and your soffits are all metal, wouldn't that kind of interfere with the antenna, with the
Well,
inductance?
It'll affect it. There's no question about it. A lot of people, and there's a couple of those famous resorts in Florida where they have all the advertisements and stuff, probably have 100 bullet antennas around the houses down there. And, they usually put them, they put them on little standoffs, 3 to 6 inch standoffs. And then they just run them around here because they really don't have any other alternative. They can't put up an antenna, so they put a really thin wire, or they have the wire the same color as the house and kind of camouflage it outside. But at least they're getting out there on the air, having fun. And it's part of the game. But yes, they will interact, but you can always compensate that with a counterpoise change or by fine tuning where you put the choke.
Okay, makes sense. Thank you.
You're welcome.
Well, we appreciate your time. Bob, you've been an amazing speaker, and we're glad you were able to come by and share your information with us. So we look forward to having you back and giving us the NFED talk next time.
Yeah, I'll give you in fact, I was prepared to do the NFED. So if you go to the website under under technical information. It'll say speaker and it'll say speaker presentations. And this talk that I gave tonight is the second one down there for the Valley of the Moon ones. But the one right above it is the NFED one. So you'll see your logo close to the NFED ones and not the other one, but they're both on there. So I'll come back and do the other one some other time. That's fine. And either way, always have fun.
All right, sounds great, Bob. Thank you again for coming and sharing your knowledge with us. And we will definitely look forward to the NFED talk.
All right, sounds good. Thanks, everybody. And
Yep.
had a good
Thank
time.
you so much.
And
Thanks a lot.
cheers and beers.
There you
All
go.
right.
7-3. Have a good dinner.
73s, everybody.
Yeah. All
All
right.
right.
73.
Bye-bye.
Thank you.
So you got it?
All right.